everyone, this is Spuggyhawk and welcome to another episode of Turtle Time. Last time we left off with a farming turtle that was harvesting crops, but it wasn't very efficient. In this episode we'll have a look at making things work better. We need to find out whether wheat is ripe before we harvest it, otherwise we'll get no wheat and we'll be back to seedlings. I've set up 3 examples here so that we can see what a turtle can find out about wheat, logs and doors. What we need is one of the inspect functions that are available from the Turtle API. There are the usual variants of the function of inspect, inspect up and inspect down. But the inspect functions return a bit more than we're used to. It seems that they return a boolean and either a table or a string. Let's have a closer look. So when we inspect the block, if there is something to inspect, the success value will be true, and we'll also get a table of information. If there's only air in the space we inspect, the success value will be false, and we'll get a string containing the error message. I'll explain tables in a minute, but let's try this out and see what the error message looks like. To get the return values, we just need to provide 2 variable names to hold the information that comes out of the function. The data variable will either hold the table or the error string. There's currently nothing in front of the turtle, so let's see what that does. That's good. The inspection failed to find anything, so success was false, and the error string was nice and clear. If I now plant some seeds, we can try that again. This time, success is true, so we have access to the information for the block. But this is in a table, and I think I should explain a bit more about that. What is a table? We don't need all the functionality of a turtle to describe this, so I thought it would make a change just to use a computer. Up until now, we've only been looking at data types that just store a single kind of information: Boolean, numeric, or a string of characters. Because they only store one kind of information, they're called simple data types. A table is a complex data type, not because it's complicated, but because it can hold more than one piece of information. An example should help us get started. Here are the first 3 letters of the Greek alphabet stored in a list called Greek. You can split the line of code up like this to make it more readable for us. The computer will ignore all the extra spaces. It's only interested in the items separated by commas between the curly braces. Let's try to print that out and see what we get. That's just a number. What does that mean? Well, that number is the memory location, or the address in memory, where the data for that table starts. Print Greek is asking the computer to tell us where Greek is, not what's in it. To find out what's in it, we need to be more specific. Tables store a list of key value pairs. What this means is that each value in the list can be accessed by a name or key. When you create a list like this, each value is automatically assigned a numeric key starting at 1. So the key of 1 will give us alpha, 2 will give us beta, and 3 will give us gamma. Of course, if we can do this in a sequence like this, we can also do it in a loop. What if we add another Greek letter, delta? Ah, the loop is still only counting from 1 to 3. We can update that to 4, but what happens if we add more letters, or take some letters away? Well, there's a way to get the number of items in the table. Putting a hash in front of the table name will give us that. That's all great, but what's this key value stuff that I mentioned earlier? All we're looking at the moment are the values that the table stores. The keys in this case are simply the numbers from 1 to 4. Let's create a table with key value pairs, where the key isn't just a number. In this case, we'll create a table with names and ages. The name will be the key, and the age will be the value. Now we've specified the key, and not just let the computer use a default number, this means that we can no longer use ages1 to get the age associated with Andy. Now we need to use the key, Andy. There are two different ways to do this. We can specify the key as a string, or we can use a cleaner dot notation. In order to loop through the contents of the table that's using the key value pairs like this, Lua provides a useful function called pairs that we can use in a for loop, like this. Previously, we've specified the range of our for loops using the start and end values separated by a comma. The in syntax lets us provide a list to the for loop. The pairs function takes a table as a parameter and returns the contents of that table as a list of keys and values. The for loop can then step through each of those key value pairs. Right, now we know how to get the information out of a table. Let's go back to the examples that I set up and write a program that can display the block data. Let's try that and see what's in the table when we inspect wheat and how that compares to the API documentation. We can see from the output that the table contains keys called state, name, and metadata. Name is the name of the block. In this case, it's Minecraft:wheat. Metadata is 0. In this case, I happen to know that's the age of the wheat. As the documentation says, the state is only available from Minecraft 1.8. If you're using an earlier version, you'll be able to use the metadata for the age of the wheat, but there won't be any state information. Finally, state is another table. But that's fine. We can add a loop inside the first one to display the contents of this table too. There are two things to bear in mind when we do this. First, we've already used the variable names key and value, so we need new names for our nested loop to avoid confusing the computer. Second, when we find the key called state, the table is stored in the value. I'll include a couple of spaces before key 2 so that it's indented a bit. Now, as we step through each key value pair that's returned from the inspect function, we'll check to see if the key is state. If it is, then we know it's a table in the value, and we'll display the key value pairs from that table as well. If it's not state, then we'll just display the key and the value. Let's see what happens. Now we can see we have the age of the wheat. But what does an age of 1 mean? In the inspect function description, we can see that state contains something called block state. That's a link to the Minecraft Gamepedia website. There's a lot of blocks that provide state information. Let's look for wheat. And that's what we're after. We have a key called age, and that's in the name column. We have a value of 1, and that's in the value column. So the age of the wheat is currently 1. When the age gets to 7, the wheat is fully grown and can be harvested. You might have noticed that wood is the next item on the list. It's also the next block in the examples that I've set up. Let's look at the block state information here, and then get the turtle to inspect an actual block. Wheat only had age information, but wood has 2, axis and variant. Let's see what the turtle can find. Great, that matches up nicely. The last one is the door. Let's see what the turtle finds before we look in the documentation. That's quite a list. Let's check the documentation to confirm what everything is. The various types of door have 5 pieces of information that we could use. The direction it's facing, whether we're looking at the top or bottom of the door, which side the hinge is on, whether it's open or closed, and whether it's got redstone power applied to it. If you can find a use for the first 3 of those, please leave a comment because I'd be very interested. So the output showed the door was closed and wasn't powered. If we throw the lever to open the door, that's applying a redstone signal. And that's confirmed in the output. Now that we've had a look at the block states, we know that when the age of the wheat is 7, we can harvest it. Let's update the farmer to make sure that he only harvests ripe wheat. Edit the farmer program and look for the harvest wheat function. In that function, we've got a loop that currently harvests all 8 wheat and replants seeds. Before we harvest the wheat, we need to check that it's ripe. Remember that we're above the wheat, so we'll use inspect down. If the inspection is successful, then we can assume that we're over wheat. Because the metadata for wheat is the same as age, we can use that as a shortcut and not bother checking the state table. If the metadata, or age, is 7, then we can harvest the wheat and plant seeds for the next crop. Make sure not to include the move forward in this test, otherwise the turtle will just grind to a halt over the first unripe wheat. Whilst we're here, we can also improve on the harvesting of other crops. For those, we always harvest directly from above. That means we can just do a quick check to see if there's anything below us before starting. This doesn't need the full power of the inspect down function. We can just use detect down instead. Detect down returns a boolean to say whether or not there's anything below us. It does mean that for cactus and sugarcane, those crops need to be fully grown to 3 blocks high before we'll harvest them, but I don't think that will be a problem. Let's check that's doing what we expect. Notice that only the last 2 wheat blocks are fully ripe. Excellent, that's just what we wanted. There's one last thing I'd like to introduce, and that's how to get turtles to automatically start their programs when you start the game. You can write a special program on a computer or turtle called Startup. When the computer or turtle first springs to life, either when you start the game or return from a long journey, it will look for that program and, if it exists, it will execute it. We could just get Startup to run the appropriate program, for example Forester or Farmer, but there's a potential problem that we need to avoid. All the programs we've written so far assume the turtle is starting from a specific location. If you exited the game when the turtle was halfway through its program, it will have stopped wherever it got to. Starting the program from there could cause a few problems. We'll develop a better solution later, but for now, let's just get the turtles to check whether they're in their starting positions. An easy way to do that will be to check that they can see the disk in the disk drive. We can check that using the File System API. fsexists will let us check to see if a file exists. For each of our turtles, we can check for their program on the disk. But how do we get this program to run another program? That's done from the Shell API. There's a function called shell.run, and you provide the name of the program to run. Note that we want to run the program that's on the turtle, not the one that's on the disk. Control R will reset the turtle and make it run the startup program. That's it for this episode. I hope you enjoyed it and I hope you found it useful. Please leave me some feedback in the comments. See you next time.